Well, the range of hydronium and hydroxide ion concentrations is very large. You can have like 10 moles per liter, or you can have like 10 to the minus 13 moles per liter, right? And so it's this huge range. That's 15 orders of magnitude or 14 orders of magnitude. It's huge. And so to compress that and make the numbers more reasonable, we developed the pH and pOH scales. And these use base 10 logarithms to make the numbers more manageable. And you've probably heard of pH. They talk about it on shampoo commercials a lot. If you have a backyard swimming pool, you know that you have to keep checking the pH of the swimming pool because otherwise things get out of whack. Your backyard swimming pool is basically like a giant chemical cauldron, right? You have to keep everything in balance or bad stuff happens, like turning green, right? So pH, if the pH is 7, that's a neutral solution. If the pH is less than 7, it's acidic. If the pH is greater than 7, it's basic. We sometimes also distinguish weakly acidic and weakly basic, and I'm not going to ask you to determine where weakly basic starts and strongly basic ends. Weakly basic is just in between here somewhere. pH 7 is neutral. High pH is basic. We often color code this as blue. Bases turn red litmus paper blue. It's also convenient that base starts with B and so does blue. Acids turn blue litmus paper red, and so that's why this is colored red. This is more acidic down here. So with logs, the logarithm is asking what power of 10 is this number? So if we have a pH of 4, the hydronium ion concentration is going to be 10 to the minus 4 moles per liter. And if we represent that as 1 dot and we change the pH from 4 to 3, the concentration of hydronium ion increases by a factor of 10. So it goes from 1 dot to 4 dots. If we go from pH 3 to pH 2, the hydronium ion concentration increases by a factor of 10. So each pH unit represents a factor of 10 in the hydronium ion concentration. A logarithmic scale is also used to measure the strength of earthquakes. And so an earthquake with a magnitude of 7 is 10 times worse than one with a magnitude of 6. And so that's why even just a couple tenths in there can make a big difference between whether your house is still standing or whether it gets flattened. So the equation that allows us to calculate the pH is this one. The pH is equal to the negative of the logarithm, base 10 logarithm of hydronium ion concentration. This negative is just multiplying by a -1. It's just changed the sign. There's no such thing as negative log. There's something called anti-log, but that's not what we're talking about here. Your calculator should have a button that's labeled log. Okay, it has nothing to do with burning wood or cutting down trees or anything. It's logarithm. So, and then here on my slides, it says, explain logarithms. This comes out different every time. So I wonder what we're going to get today. So get your calculator out if you don't already have it out. Get it turned on and find that log button. So type in 1,000. Some calculators, you have to press the log button first and then put in the number. Others, you put the number in and then you press the log button. But find the base 10 log of 1,000. What does your calculator say? 3. So the log, let's start this again. The base 10 log of 1,000. So I have a TI-36X Pro, and so what I do is I press this has an ln log button, and I have to press that twice. The first time gives me ln, which is natural log. We're not going to do those. Press it twice to get log, and then I put the number in. Other calculators, you might put in 1,000 and then press the log button. So the log of 1,000 is 3. Well, 1,000, if we express that as 10 to the something, what would it be? 10 to the third. 1,000 is the same as 10 to the 3. It's 10 times itself 3 times. So finding the log of 1,000 is finding the exponent on 10 that's equivalent to this number. So if we're just dealing with ones and zeros, we can do this without a calculator. What if I had the log of 1, 2, 3, 4, 5 zeros in there? The log of that is 5. Okay, because that equals 10 to the 5th. Well, let's try a smaller number. Let's take the log of 0.01. You get -2. So the log of that number is -2. If we express this as an exponent of 10, 0.01, moving this 2 places, that's the same as 10 to the -2. So if we had 10 to the -7, the concentration of hydronium ion and hydroxide ion in a neutral solution. The log of, you'd want to enter it as 1 times 10 to the -7. That's going to give you -7. That's not the pH. pH is the negative of the log of that. So if I take this number and multiply by -1, what do I get? I get +7, right? So the negative log of 1 times 10 to the -7 is +7. The reason that the minus sign is in here is because all of these are going to end up being negative unless we put the negative sign in there. We don't like dealing with negative numbers unless we really have to. So pH is -1 times the log of whatever. Well, let's look at what about 1 times 10 to the -6th molar or something? The log of 10 to the -6 is -6, right? And the log, and then you just change the sign, and so this should give you 6. Seeing some puzzled looks. I don't want to lose you just yet. I'll lose you later, but not now. You have questions? Can you make your calculator do it?
Yes.
Good. How are you entering, if it's giving you 5, how are you entering the 1 times 10 to the -6?
10E, which are 2E's.
You want to use the EE button? 1 EE minus 6. And then take the log of that. Anybody else have any questions? If you're having trouble with your calculator and don't want to say anything about it now, please come and talk to me afterwards, because it's a very simple fix and it'll save you lots of points on exams. What if we have something a little trickier? What if we do the negative log of 1.5 times 10 to the -7? So negative log 1.5 EE minus 7. So my calculator is telling me 6.8. 2 and some more digits. So the pH of a 1 times 10 to the minus 7 molar hydronium ion solution is 7. The pH of 1 times 10 to the minus 6 is 6. 1.5 times 10 to the minus 7 is between these two numbers, and so the pH is between 6 and 7. But it's not linear. It's not linear at all. Any questions? So calculate the pH of each solution. Indicate whether it's acidic or basic. Now you can look at the concentrations and determine whether it's acidic or basic by comparing and asking, is this hydronium ion concentration greater or less than 10 to the minus 7? That's a little tricky though because of all those negatives, and it's kind of tricky, is it bigger or smaller? I think it's easier to compare the pHs because those end up being positive numbers. But let's do this calculation. So pH equals the negative log of the hydronium ion concentration. So it's the negative log of 9.5 times 10 to the minus 9. So on my calculator, I'm going to put the negative sign in, not the minus sign, but the negative sign. I'm going to press my natural log button twice so that it shows me log. Then I'm going to put in 9.5 EE minus 9 and press equals. And it's going to give me 8.02 as the pH. I'll tell you about the sig figs in a few minutes. Can you get your calculator to give you the correct number? If you have a calculator that uses the other kind of logic, you're going to put in the 9.5 EE minus 9, then you're going to press the log button, and then you're going to press the change sign button. So some calculators you work forward, some you work backwards. Is this acidic or basic? It's basic. High pH is basic, low pH is acidic. So this is basic. And then let's do this one. Hydronium ion concentration is 6.1 times 10 to the minus 3. So the pH equals the negative log of 6.1 times 10 to the minus 3. This is going to be a 2 something, 2 point something. 2 point what?
2.2146.
Actually, 2.2 is all I, no, 2.21. I do need 2 digits. 2.21. Acidic or basic? Acidic. Yeah, this is the hydronium ion concentration. This is higher than 10 to the minus 7, so it's acidic. The pH is lower than 7, so it's acidic. I would recommend choosing one of those and sticking to it instead of trying to do both, because they sort of seem opposite. Any questions? What if we know what the pH is, but we want the hydronium ion concentration? Well, then we have to undo the equation. And so I'm going to show this to you real quick. This is a slide where if I lose you, it's okay. So I'm just going to show you where this equation comes from. So there's our pH equation. If we want to know the hydronium ion concentration from the pH, we have to rearrange this. We have to solve it for the hydronium ion concentration. So I'm going to move this negative sign over here, multiply both by -1. To undo the logarithm, I have to do the anti-log. 10 to the x is the anti-log. So I get 10 to the x of both sides. So 10 to the negative pH is equal 10 to the log of the hydronium ion concentration. and these two cancel out, and that is equal to the hydronium ion concentration. So if you care about where that came from, there it is. If you don't care, don't worry. There's the equation. This is the equation right here. So calculate the hydronium ion concentration for a solution with a pH of 8.37. We need to use that new equation because we have the pH, but we need to know what the hydronium ion concentration is. So hydronium ion concentration equals 10 to the negative pH. So 10 raised to the negative 8.37 power. And you might not be used to seeing non-integers as exponents, but you can do it. There is a 10 to the x button on your calculator that I've told you not to use for scientific notation. This is where we want to use the 10 to the x button. That's the anti-log button. That undoes a logarithm. So on my calculator, I have a button that's like E with a square and 10 with a square. And so if I press it twice, I get the 10 raised to the, and then I put in negative 8.37 and press equals, and I get this crazy small number that I have to mess with scientific notation for. And so this is going to give me 4.3 times 10 to the minus 9, and I'm going to slap the unit molarity on there, because these are always done with units of molarity on the concentrations. Can you get that number? It's good to practice on ones where we know what the answer's supposed to be before you start to do a worksheet or homework, and so you can fix your mistakes before you start losing points. Any questions? We use this p, this lowercase p, it's a function really. It's the negative log of whatever comes after it. So pOH is equal to the negative log of the hydroxide ion concentration. Same equation applied to hydroxide instead of hydronium. And there's actually a very nice relationship between pH and pOH. So I'm going to derive that for those of you who care. So we know that the hydronium ion concentration times the hydroxide ion concentration is equal to 1 times 10 to the minus 14. That's the equilibrium expression for the self-ionization of water. So P means negative log of. Well, so what I'm going to do is I'm going to take the logarithm of both sides. So if I take the logarithm of this side, if you take the log of numbers that are multiplied, then you are going to be adding. So I'm going to have the log of hydronium plus the log of hydroxide is equal to the log of 10 to the minus 14. Well, the log of 10 to the minus 14 is negative 14. And then I'm going to multiply the whole thing by minus 1. So I'm going to get negative log of the hydronium ion concentration and negative plus the negative log of the hydroxide ion concentration is equal to 14. Well, that's an ugly H. What's the other representation for negative log of hydronium ion concentration? What's the other representation for the negative log of hydroxide ion concentration? That is pOH. So instead of writing out that mass, I'm going to write pOH. Negative log of hydronium ion concentration is the pH. So I've got pH plus pOH equals 14. I like that one. There's no exponents or anything in it. Just adding. So before I get, I want to show you, you've heard of the circle of life, right? Lion King, the circle of life. There's a circle of pH. And we've discussed several different equations here, and they are related. So the pH is related to the hydronium ion concentration. The hydronium ion concentration is related to the hydroxide ion concentration. And the hydroxide ion concentration is related to pOH. And pOH is related to pH. You know, it's almost a circle. So this relationship is pH plus pOH is equal to 14. If you know one, you can find the other. If I know this one, I can find this one using that equation. pH and pOH we got our basic pH equation, or the opposite of it, rearranged. Hydronium ion concentration 10 to the negative pH. The relationship between hydronium and hydroxide ion is that you multiply them and they equal 10 to the minus 14. And the relationship between pOH and hydroxide ion concentration is very similar to pH and hydronium ion concentration. The circle of pH. There it is. Any questions? Okay, so let's do this example. Calculate hydroxide ion concentration if the pOH is 4.25. Well, what equation do we need? What are they asking us to find? They're asking for hydroxide, so we need an equation that says hydroxide ion concentration equals something. And it has to have pOH in it. So 10 to the negative pOH. So that's going to be 10 to the negative 4.25. 5.6 times 10 to the negative fifth. Any questions? Yes? 10 to the x. On some calculators, you have to press the 10 to the x button first and then put in negative 4.25. Other ones, you put in negative 4.25 and then press 10 to the x. Any questions?